talking in the distinguished seminar. Eric is producing some of the most exciting research in statistics now, well, for some years now. He's an expert in mathematical statistics, especially in semi-parametric models and causal inference. He has a PhD in biostat from Harvard. He was faculty there for many years, so he's not a stranger to the statistics and causal inference community in the Boston area. And something that I learned today that I didn't know about you, Eric, is that you have a bachelor's degree in electrical engineering, like from Yale, like so very, you know, a very IDSS type of bio. So we are very excited to have you here, and please, like, take it away.
Thank you, Alberto. Thank you so much for having me here today. I'm really excited to present this work. Let me see if I can suppress this top thing. All right. So my talk is an introduction to proximal causal learning. This is kind of an introductory talk to some work that I've been doing with a group of postdoc students and faculty for the last 2 to 3 years. And we finally have some interesting results that we would like to share today. So first, an outline of my talk. I'll start off with some preliminary review of exchangeability and concepts of exchangeability in causal inference. Everyone would probably be familiar with that. I'm going to discuss it a little differently just to set up the framework. And then the goal of today is to introduce an alternative to exchangeability, which we call proximal causal inference. And we're going to argue that in most cases where people are actually defend exchangeability, and exchangeability comes in different names, under different names. Non-measure confounding, selection on observables. The idea is you have sufficient covariates that you can assume that the treatment arms are essentially exchangeable with respect to the potential outcomes, are independent of the potential outcomes condition of those covariates. So we'll present an alternative to that. And the basic idea is that in most cases where people argue that they have exchangeability, what we're going to argue is that at best they have proxies of the real underlying confounding mechanism. And so this framework will allow you to operate under that setup, where you no longer require exchangeability, you're going to require something else. And you're going to require essentially what we'll define as valid proxies. And then go through identification, provide identification conditions, and then a little bit of estimation that I'm going to do today. We'll present an application which I'll introduce early on in the talk as motivation for some of this work, and then with some concluding remarks. So these are the member of the Proximal Inference Group, the PI group. We have 2 postdocs currently working with me, Andre Ying and Yifan Cui. They're both at Wharton. A former postdoc who was at Harvard, actually, was a data science postdoc at Harvard, Shushi, and Wang Yao, who she's now a faculty. Shu is a faculty at UMich. Wang is a faculty at Peking U. He was a postdoc of mine as well. And then Homing Pu, who is actually a student of Tony Kai, but he's kind of a jack of all trades, and he wanted to learn a little bit about semi-parametric theory and causal inference. And so he's working more on the minimax type questions under this framework. If you find anything interesting and innovative in this work, it's really due to these outstanding group of collaborators I have. And any errors will have to be my own. They're a lot more careful than I am often. So as we know, studies in the social and health sciences commonly aim to determine the causal effect of a point or time-varying treatment. Now, I should say everything I'm going to present here works as well for so-called panel data or longitudinal data, where you might be interested in the effect of a joint intervention over time. But I will focus, just for clarity, on point exposure. I'll make some remarks about that towards the end of the talk. Although ideally, we would love to run a double-blind randomized study And often in practice, we cannot for ethical or practical reasons. Standard assumption for causal inference from observational data is that one has measured a sufficiently rich set of covariates to ensure that within covariate strata, subjects are exchangeable across observed treatment values. Skepticism about the exchangeability assumption in observational study is often well warranted, and that's because the assumption hinges on an investigator's ability to accurately measure covariates capturing all potential sources of confounding. Realistically, if we're being completely honest with ourselves, confounding mechanisms can rarely, if ever, be learned with certainty from measured covariates. And so this is something that we often rely on this assumption because it's convenient, and sometimes we might do alternative analyses, would anchor analysis on such an assumption and enrich it with other kinds of analyses. And the point is that even anchoring analysis on this exchangeability assumption is often not a credible assumption or a reasonable thing to do. So what we're going to argue is that the most that one can hope for in practice is that covariate measurements are at best really good proxies of the true underlying confounding mechanism operating in a given observational study. Once you acknowledge that, any causal claims made on the basis of exchangeability become invalid. So in today's talk, I'm going to introduce a general framework for proximal causal learning, which, while explicitly acknowledging covariate measurements as imperfect proxies of confounding mechanisms, enables one to potentially learn about causal effects in settings where exchangeability does not hold on the basis of measured covariates. So I want to introduce a running example I'm going to use and often refer to throughout the talk. This is a data set that's well known to the causal inference community. This is a reanalysis of a support study with the aim of evaluating the causal effect of right heart catheterization during the initial care of critically ill patients in intensive care units on 30-day survival. This was an analysis that was initially published in '96 by Corners and colleagues, and have been realized by many folks using various kinds of causal methods. Primarily, actually, I would say in kind of methodological developers who want to showcase their new technique, they often use this data set. Going back to the original study, it was actually kind of interesting to go back and read about what happened in this study and what the kind of controversy around this study. So RHC, right heart catheterization, was performed in study on a little over 2,000 patients within the initial 24 hours of ICU stay, while a little over 3,500 patients were managed without RHC. So RHC will be our treatment and no RHC our control. So in their paper, Connors et al. Were concerned that patients for whom RHC was performed might have been a lot sicker than those who were not offered RHC. And so just the selection bias or confounding bias might show harmful effect of RHC even under the null or protective effect of RHC. So that was a concern. So the study fortunately collected a rich set of information on patients, included in 73 covariates, including demographics, including probability of survival based on some variables, comorbidity, vital signs, physiological status, and functional status. The authors then performed propensity score matching, that was the analysis, using all 73 covariates, this data set. And what they found was that the effect of RHC was significantly harmful for survival. But this was actually something that appeared not to help the patients, but actually to harm them relative to 30-day survival. And you can imagine RHC at the time was kind of, I believe Nobel Prize had been won because of by the doctors who had developed the procedure, and there was much talk about it. And so this really sent a shockwaves in cardiology community. Okay. Supporters argued that there were two camps, obviously. The supporters who argued that surely accounting for 73 variables must definitely render the RHC arm indistinguishable from the no RHC arm at baseline, which is obviously not a testable assumption empirically. But they thought this is sufficiently rich set of covariates. Why be concerned about confounding bias after adjusting for such a rich set of covariates? And skeptics called in question their ability to account for strong selection bias into RHC arm, even after adjusting for 73 observed covariates. There must still remain some unmeasured confounding, such that the RHC patients might not have been exchangeable with the no RHC patients. Interestingly, the debate was never really entirely resolved to this day. Quite a few papers in causal inference have reanalyzed the support data, and the findings appear robust to the choice of analysis. But I should say still, the large minority of analyses rely on exchangeability. Okay, so it's like the new kind of way of adjusting for covariates. They throw the data, they throw the algorithm at the data, and then they get an answer, and it consistently shows a harmful effect, no matter how you adjust for covariates. I do have to say that if you're really alarmed by this, RHC is actually something that is known to work really well. And over the years, it's been the technique has been well developed, refined, and it's a life-saving procedure. If I ever were sick enough to be considered for it, I would want to receive RHC. And so there's something, just to reassure you, this is a very specific kind of study. It was a really, really, really sick population in the first place. And this was those days where it was still relatively novel in terms of practice. So practice has evolved since then. You might also be interested to know that there was a randomized trial to evaluate actually the causal effect of RHC, and it found it was unable to reject the null. So there was no evidence in that randomized trial of any harmful or protective effect of RHC. And I should granted that this was in a different population. It was not as sick of a population, because that was not the appropriate for a randomized trial. And so it is possible these two facts are not necessarily mutually exclusive. It's possible that that, as I said, the population was quite different, and the practice of RHC was also quite different from what we have today. Okay, it's kind of the gold standard when you are undergoing you have heart issues and you need hospitalization. All right, so you have beta into the ICU. So let's formalize the framework. So brief review of exchangeability. I apologize, this might be a little boring, but let's just make sure that we're all on the same page in terms of notation. Suppose we observed ID samples, A, Y, and L. A is going to denote our treatment of interest, so RC. Y is an outcome of interest, like 30-day survival, and L is a set of measured covariates. We'll use the potential outcome framework. So Y little a denotes the potential outcome had possibly contrary to fact a person received treatment little a. We aim to identify a population average causal effect corresponding to a contrast of counterfactual averages, which I'll refer to as beta A for little a, for different values of A. For example, in case of binary treatment, you might look at an additive causal effect. And we don't necessarily restricting ourselves to binary treatment, I should say. Okay. In case of binary outcome, you might look at a multiplicative causal effect. In all cases, whether A is binary, polyphemous, or continuous, we need to identify a potential outcome mean beta A from the observed sample. So it suffices to make this talk about beta A, not necessarily whatever scale you're interested in measuring an average causal effect. So what are the standard assumptions for identification of beta A? It's typically assumed that consistency holds, that you observe Y matches your potential outcome under the observed treatment value, and there should be an almost surely here. This encodes the assumptions in SUDVA, so if you prefer to use SUDVA, it gives you the same thing. I just like the simplicity of stating this assumption. We assume will assume positivity that for a given value of A of interest, for any value of L that are realized in the population, at least some of the individuals with that value of L will uptake the treatment, little a. And then exchangeability, or assumption of known measure confounding on the basis of measured covariate. Okay, that conditional covariate is as if treatment were randomized and therefore independent of all pre-treatment variable, the potential outcome being the most relevant predictor of your outcome and baseline covariate. And so your treatment will be independent of your potential outcome. Conditional on measured covariate. So that's our assumption of known measure confounding or exchangeability, conditional exchangeability. Under these three assumptions, it's well known that beta A is identified by this formula. This is the simplest instance of a formula most commonly known in the field of biostatistics and epidemiology as a G formula. It's known under different names in different disciplines. The G formula is usually associated with the work of Jamie Robbins. And I'm going to adopt this because Jamie generalizes to many settings and was interested in all of those settings, including time-varying treatment with time-varying confounding. And so, as it turns out, the proximal causal inference framework extends to that setting. So we'll borrow this name G formula. We'll just append a proximal G formula in front of it once we identify it, as I will show a little later. All right. So this assumption is usually, if you're familiar with DAGs, they're very useful to kind of understand under what conditions does this assumption make sense. So I'm going to present some alternative data generating mechanisms under which exchangeability holds, and these are illustrated in these three DAGs. In the first one, so A is our treatment, Y outcome, L are measured covariates. In figure A, L includes all common causes of A and Y, and we'll sometimes refer to that as being a covariate of type A. Okay, and if you've measured L here, you have non-measure confounding because you can block all backdoor path by conditioning on L. Okay, using this separation criteria in graphical causal model, you identify the causal effect of A on Y. In figure B, L is of type B, which includes all causes of A that share an unmeasured common cause U with Y, and therefore associated with Y, although they do not cause Y. Okay, so A here, L is not a cause of Y, but it's a really, really good proxy of the actual unmeasured confounding variable. It's really, really good. It's kind of an ideal proxy in the sense that it actually it blocks all paths from U to A, and therefore allows you to identify the average causal effect. In figure C, L is of type C, which includes all causes of Y that share an unmeasured common cause with A, and therefore associated with A, although they do not cause A. So this is kind of the mirror of this. Okay, so L are causes of Y. They're not causes of A, but they share an unmeasured common cause with A, G and L. So in all these three cases, we can exchangeability actually can be shown to hold. So these are just examples. In practice, we never really care as to which one of these cases holds. And there are many more cases you could draw. Okay, so I'm just giving you some illustration of three because they're connected to the rest of my talk. These three possibilities may coexist, as displayed in figure D, in which L has now been decomposed into three bucket types of measured covariates. We have our type A, X. We have a type Z, measured covariates of type B. So Z are causes of A that share an unmeasured common cause with Y. And W of type C, W are all causes of Y that share an unmeasured common cause with A. Okay. These four DAGs illustrate possible data generating mechanisms under which exchangeability holds, without necessarily requiring that the analyst identify which bucket type each covariate L belongs to. Importantly, all settings considered thus far rule out the presence of unmeasured confounding conditional on Z, X, and W. And so we don't really care which bucket type any variable might be in. Okay, but if we're willing to rule out unmeasured confounding conditional on L, we can ignore all of these graphs. When are these graphs ever helpful? Well, note that in order for exchangeability to hold in figure D, the most complicated figure I've presented so far, it must be that, as encoded in the DAG, unmeasured variables U1 and U2 are independent conditional on A, X, and Z. Otherwise, as is illustrated in this graph, we have now added a common cause between U1 and U2, which is also not observed. The unblocked backdoor path from A, U2, U3, U1, and Y would invalidate exchangeability. Okay, it would correlate the two, A and Y, even under the null of no effect of A on Y, conditional on Z, X, and W. And so those exchangeability obviously rules out that there's such a U3. As we show next, it is sometimes possible to relax this last assumption that there is no unmeasured common cause between U1 and U2. In fact, you can actually relax it considerably. And therefore, to relax exchangeability condition 3, while preserving identification of beta A, despite the presence of unmeasured confounding, provided that one can correctly identify which bucket type each measured covariate falls into. So that's basically what we're going to do. We're going to replace exchangeability, and then we're going to assign our proxies to be a certain type. And what we're going to argue is that this is actually something quite reasonable to reason about, if you will. This is something that you can discuss with your colleague and reason through, acknowledging that you have not measured your target on measure confounding. You have a rich set of covariates. And the question is, can I reason through assigning these proxies? Now, a few remarks. So figures 2 and 3 that I'm giving here now depict settings in which exchangeability fails despite having measured L. So I've pulled the U's into one U. So this is displaying now, we have unmeasured confounding of the effect of E on Y, that's U. Okay. But we now have been able to decompose these variables into Z, X, and W. Okay. So we're going to propose to replace the untestable exchangeability assumption with the assumption that the analyst has correctly identified variable Z in bucket type B, potential treatment, which we'll refer to as potential treatment inducing confounding proxies. So these are variables that are not causes of Y. They're only correlated with Y because they are proxies of the actual underlying unmeasured confounder. They may cause A. They don't have to cause A. Okay, they don't have to be relevant for A. They need to only be correlated with U. And so that's what's displayed in this graph. And we'll argue that it's actually often the case that this is a situation that presents itself. That you can enrich U enough that such that Z is not correlated with A, given U, X, and W is not correlated with Y, given U, X. Okay, and so the underlying assumption I'm actually going to rely on, we're going to replace exchangeability with the following two conditions. And these are going to be conditions that define our proxies. So we have a treatment inducing confounding proxy, Z, which is independent of Y, conditional on A, X, and the underlying confounding factor U. So this is saying it's a proxy in the sense that if I had measured the unmeasured confounder, it would not provide any information about Y. It needs to be relevant to be useful. So you will see that, in fact, we'll assume that Z is actually associated with U, conditional on A and X. Okay.
Eric, could I ask a quick clarifying question?
Sure.
Apologies if I missed this. Up until now, have you made any assumptions about the structural causal models, for example, linear versus nonlinear?
No.
All right, thank you.
No, everything is going to be nonparametric. In the next slide, I'm going to introduce the basic idea for identification in a simple linear structural model. And then after that, the rest of the talk is going to be going back to the nonparametric model. And I'll draw some connection to the NPIV, to the nonparametric IV problem, because there's some interesting relationship to that problem. So that was our proxy. So there's no parametric model in our mind. We're only making these assumptions that are not testable, note, because obviously the condition on the unmeasured confounder, but they encode this idea of proxies. If I was thinking of Z as either a mismeasured or a variable that really tries to measure, like I'm trying to measure the confounding mechanisms that's due to smoking, because I'm trying to assess the causal effect of BMI on depression, and smoking is an important confounder. There are many ways I can measure smoking. I can ask a person, how often do you smoke if you're a smoker? Did you ever smoke in the past? Do you only smoke when you're drinking? there are many variables, and certainly none of them is the real measurement of the underlying confounding mechanisms that's due to smoking. But we have a bunch of proxies. Okay, and so the idea is that if those proxies would be independent of Y, if I were to condition on A, U, and X. Likewise, we have a second kind of proxy, W. W we'll refer to it as an outcome-inducing confounding proxy in the sense that we require it to be independent of the treatment and of Z, conditional on U and X. Okay, and these are two decks that illustrate this idea. And so the treatment and Z should be deseparated from W, conditional on U and X. Okay. In this graph, Z and W are fungible. Doesn't matter which you pick for which rule. In this graph, they're not fungible. When is this an important distinction? Well, let's take an example, a concrete example, like in HIV studies. In HIV studies, it's known that doctors measure CD4 count. I mean, it used to be the case before universal test and treat, that doctors will decide to treat a patient based on their measurement of CD4 count. Now, CD4 count is an important confounder, therefore, because CD4 count will determine whether the patient starts the treatment, but it also determines disease progression. Now, it's very clear that CD4 count, this CD4 count itself is not the true underlying CD4 count that matters to the immune system for the patient, right? It's measured with error, it's measured at one time point. What we need is an understanding of the evolution of the immune system over time. That's the underlying confounder. However, Z is used by the physician to decide whether or not to treat the patient, therefore Z causes A. But the underlying unmeasured confounding is actually not observed, and Z is a correlate of it. Okay. In many other examples, for instance, in the setting where people typically will go to think about difference in differences as a method of analysis, okay, the argument is that in fact that baseline measurement of the outcome is in fact an outcome proxy. Okay, so that would be our measurement of W. And because it's a measurement of W, it might actually be a cause of Y if it's measured at 2 time points. So it might be the case, as I said, that you can be rich such that the DAG in figure 3 actually holds. Examples of proxies of type B and C abound in observational studies. I'm going to give a few very quickly. As I said, in observational studies evaluating the effects of a treatment on disease progression, the general concern that patients either that patients either self-select according to health-seeking behavior or are selected by their physician to take their treatment based on prognostic factors for the outcome. A diligent investigator will endeavor to record lab measurements and other clinically relevant covariates data available to the physician and the patient when considering treatment options. This is typically done via questionnaires or by measuring biomarkers in the lab, both of which give a measurement error-prone snapshot of an underlying physiological mechanism of disease status at the source of confounding bias. Measured covariates in health and social sciences are often proxies of type B or C. For example, CD4 count and viral load in HIV research, ICD-9 codes to measure comorbidities in comparative effectiveness research, food frequency questionnaires, cognitive functioning screening tools such as the MMSC, and so on and so forth. We could spend all night just naming examples of such measurements that we routinely do in observational study when we interact with patients or participants. Other prominent applications of the proximal study design, the PSD. IV combined with difference in differences is a standard approach to address violation of IV independence assumption. So what the proximal study design will tell you to do is that you use the IV as Z. So an IV is actually a valid proxy for Z, and an invalid IV, which one that is confounded, is also a valid proxy. Okay. And baseline outcome measure is W in this case, as I mentioned earlier. Thus, rather than relying on the usual parametric assumptions of difference in differences, one can actually get from PSD non-parametric identification using this framework. Time series studies, so this is an example I really like because it's quite compelling. So people are interested in the effect of air pollution on mortality or elderly hospitalization. The usual setup is they have time series of air pollution, weekly or daily, and likewise for mortality or hospitalization in the elderly, and they correlate the two. And so they're concerned about confounding. So what the setup is going to tell you to do is, in fact, you don't have to measure any additional covariance. What you would do is you can take, so air pollution at time t on yt plus 1, that's the effect I'm interested in. I'm just looking at one cross-sectional, and you'll do this all the time, obviously. Then you can take zt to be the air pollution, the future air pollution measurement, the next time. Okay, the time after you've measured your outcome. That can now causally affect the outcome, so there's no error from that. And if you have an underlying process ut, that will be correlated with ut, okay, because it confounds your air pollution. So it's going to confound your future air pollution as well. And one can likewise take your baseline measurement of mortality, so yt, if I'm looking at as a wt. And so that's what you would do in a difference in differences approach. The point is that in air pollutions, this setup will allow you to actually have two proxies that will fit into this framework. And what we'll show is under our assumptions, you could non-parametrically identify the causal effect of air pollution and mortality. The other setups that are related to this framework: remove unwanted variation, RUV, and GWAS. There you take a large panel of genetic variants known to have null effects on the outcome, split as Z and W, and then you will run the analysis I will describe. Synthetic controls, Alberto synthetic controls actually are related to, can be related to proximal. So we have a proximal synthetic control study design, where what we essentially do is we use a pool, we take the pool of donors, and it turns out that for them to be valid donors, they must be proxies. Okay, so the issue, the appeal here is whether you have really complicated endogeneity, okay, that you want to account for. And what you do is you split that pool of donors. You use half of them as donors, genuine donor, to represent the potential outcome. And typically that's done in a linear model as a convex combination of the donors. And then you use the second half, Z, to actually identify the causal effect in a manner that I'm going to describe later on. So we have some work in progress that tries to do this. And the idea behind that was we wanted a single analysis that would allow us to get identification, inference, efficiency, if we could map it to this framework. And that's what this work has allowed us to do in the synthetic control framework. All right, so let's talk about the actual, how are we going to use these assumptions to identify causal effect despite having unmeasured confounding. So it's actually really simple, and it's best described in a linear model, right? The linear model is always our go-to model. We get all our intuitions from it. And here's how it works. So in order to ground ideas, we've briefly described the proposed proximal approach in the context of a system of structural linear models compatible with the DAG in figure 2, this DAG. So I have an outcome model. My data stream mechanism is a linear model for the outcome. I believe the world is linear, where I have condition on U, and therefore Z should not cause Y. And so the right-hand side, I have no interaction, no nonlinearities. Beautiful. And U is my unmeasured confounder. Beta A is my causal effect of interest. And then I likewise have a linear model for the outcome proxy, W, conditional on U. Because I'm conditional on U, A and Z should be independent of W. And so I have this linear equation. Okay, so the causal effect of interest is beta A. Then one can show that simply by collapsing. If you take the mean of W given A, Z, and X, you get the mean of U given A, Z, and X here. You solve for the mean of U given A, Z, and X in terms of the mean of W given A, Z, and X. You can run the regression of W given A, Z, and X. You get a solution for the mean of U given A, Z, and X. You do the same thing here. You regress Y on A, Z, and X. You collapse over U. You get the mean of U given A, Z, and X. You solve for it there. You replace it there. And below, this is what you get. Very familiar, very similar to the ID, and I will explain the connection later. And so what this tells us is that if you were to believe this model and you had valid proxies, you regress Y on A, Z, and X, and you adjust for the regression of W on A, Z, and X. And the coefficient going with beta A will then, under these assumptions, identify the causal effect of interest. So let W hat denote an asymptotic unbiased estimator of the mean of W given A, Z, and X, obtained by regressing W and A, Z, and X. Then least squares, then you run the least squares linear regression of Y on A, X, and W hat. And this will recover a slope coefficient of A, beta hat A, that can be shown to be consistent for the causal effect beta A. And there are some assumptions here. The assumption, the crucial one, is that the mean of U given in the X better depend on Z. You better have a valid and a good proxy. This is kind of the proxy relevance, sort of the IV relevance version of this. As adjusting for W hat, the bias is the least squares estimator of beta A conditional on X. We shall refer to W hat in this linear setup as a proximal confounding control variable. Okay. What's the connection to IV? The connection to IV here is interesting. What the connection to IV tells us is that, in fact, rather than usually we do an IV on A, and we'll find an IV Z of A, and then we'll do two-stage squares. What this is telling you is you find a representation of Y that depends on W. And the weights that are assigned to W in that regression, you identify them using Z as an IV for those weights. And so you moved the identify assumption from beta to identifying W. Once you've identified the coefficient that goes with W, it turns out beta A is identified. Okay. And what's remarkable here is that you don't need to model U at all. Okay. So there's this whole literature about latent factor models where they try to identify, actually estimate U. And as interesting as that is, this is completely bypassed by just stating these assumptions in this formal way. The system of linear structure equations considered above is overly restrictive, obviously. Assuming linearity and no interactions, as we now show, these assumptions are not strictly necessary and can be relaxed considerably so that nonparametric identification remains possible under certain conditions. So I'm running a little late behind, so I'm going to skip some slides. I'll let you know when I skip them that are not really essential. So here's the important part. So let's talk about nonparametric identification. So the first assumption is that there is a solution to a certain integral equation. So here's an integral equation. You run Y on A, Z, and X. You estimate the density of W given A, Z, and X. And you want to find an object, a function of A, X, and W, that solves this integral equation. So our first assumption is that there is one such solution. So this is a Freedom equation of the first kind. The necessary and sufficient conditions for the existence of a solution are very well understood. These types of integrals appear in NPIV, in the nonparametric IV literature, and so there's nothing new here. These conditions are very well understood in functional analysis. And I'm going to use some, even if they stand for integrals, just easy on the eye. All right, assumption 2, let's suppose that the following conditions hold for any function V. The conditional mean of V and V may depend on A, Z, and X. Conditional on A, Z, and X is equal to 0 if and only V is 0. This is also a familiar assumption. It's known as the completeness condition, also familiar in the IV literature. And this is not a testable assumption. It involves U. So this is a testable assumption. This is not a testable assumption. Okay. So what is our result? Given the valid confounding proxies that satisfy those two conditional independencies that I stated, that Z is independent of Y given A, X, and U, and that W is independent of A and Z given X and U. Those are the assumptions of what I mean by valid confounding proxies. Assumption 1 and assumption 2 imply that the counterfactual mean, beta A, is identified by the following integral. You take your solution from assumption 1, it need not be unique, any of the solution, and you marginalize over W and X. Okay, so that's our first result. That point identifies beta A, non-parametrically. The second result is an interesting result because it shows how the model bridges to the unmeasured confounding world, is that this function H, which we'll call a confounding bridge function, is a solution to another integral equation where the left-hand side we replaced, it looks like very much like this integral equation, but we replaced the left-hand side with one where we condition on U and the potential outcome. And the right-hand side we replace the density of W given A, Z, and X with the density of W given U and X. And so this is a really interesting representation because this is in fact, if you think of this in terms of synthetic controls, this is really all that's going on. It's saying if there exists a representation of this regression in terms of H, that representation of our assumptions actually can serve as a proxy for your potential outcome, just like with synthetic controls. Synthetic controls just find a representation of potential outcome had the treatment not been applied to the treated unit in terms of the donors. And so you can think of this as a non-parametric representation of that exists. And it's telling you that that representation would also exist conditionally on measured factor. We refer to the identifying formula of beta A as a proximal G formula. So this will be our proximal G formula. And to H of A XW as the outcome rich function. Note that the standard G formula is recovered on the exchangeability given X and W, in which case the solution is just the mean of Y given A, X, and W. Let me just say a few words about the assumptions. There are two key assumptions here. The integral equation that we have to solve is known as the Freedom equation of the first kind. Mathematical conditions for existence of a solution are well understood in functional analysis using the singular value decomposition of compact operators, and we discussed this in this paper we published a couple of years ago. The second condition is also a well-known completeness condition familiar to statisticians, which can accommodate both categorical and continuous confounders. Completeness is a technical condition which relates the range of U to that of Z, and essentially states that the set of proxies must have sufficient variability relative to variability of U. Let me just say very briefly, the conditions are easiest understood in the case of categorical U, Z, and W, with number of categories DU, DZ, and DW, respectively. In this case, completeness requires that in fact, Z and W must have at least as many categories as U. Okay, so this is a really important point. So nothing is free. You need to have strong proxies and they need to be rich enough. So the intuition here is that accounting for unmeasured confounding in the categorical case requires that the number of categories of U is no larger than that of either proxy Z and W. And that completely makes sense. And this is good because, in fact, this condition provides a rationale for measuring a rich set of baseline characteristics, which is what everyone tells you to do in observational studies as a potential strategy for mitigating unmeasured confounding via the proximal approach. We just have to be careful enough when we measure them that we don't necessarily attain exchangeability, but at least we have good proxies. Let me skip this. This is just an example where we get a closed form solution in the binary case, but I'm running really behind. So I'm going to skip all of this and then talk about the inference. Now we have parametric, semi-parametric, and non-parametric methods for inference. For this forum, I'm going to focus on the parametric approach, and then I can refer people to the relevant papers if they're interested in the other kind of more mathematical or involved approaches. So the parametric approach entails positing a model for the outcome confounding bridge. So let me just say something. This I need to say. The proximal G formula is not always available in closed form. In the discrete case, we show that it's available in closed form. Okay, and it requires solving that integral equation of the first kind, the Freedom equation of the first kind. And this is a well-known ill-posed inverse problem that is generally computationally intensive and unstable in the sense that the solution, even if it exists, will often be discontinuous in terms of the observed data distribution. So any perturbation in your estimate will lead to huge perturbation in your solution. So usually you have to regularize the problem. So we actually just described here a simple statistical modeling approach analogous to parametric G computation, which sidesteps this difficulty by regularizing the inverse problem. Okay, so there are many ways of regularizing. We just did one that's more statistical. We just model things. So here's the simple approach. The approach entails positing a model for the outcome confounding bridge function. So the idea is that you're going to assume a priori that, as in the case of synthetic controls, where it's assumed that essentially the confounding bridge function lives in a linear space, you're going to assume a parametric model for H. And you're going to solve for, and you're going to make inferences under that assumption. Okay. Just briefly, this is relaxable, and I'll come back to this a little later. Let me just describe what happens. So, your unknown parameter of H is eta, and you also have a joint law for L and A, which you have to model here. So this is a pain. You model the joint law of L and A. So you're doing maximum likelihood estimation. We don't know parameter theta. And together, these two models by the integral equation imply a model for the mean of Y given AZ and X in terms of eta and theta. And so one can then estimate eta and theta via direct maximum likelihood to yield parametric proximal G computation. So you get an estimate of the eta and you plug it into the substitution, you get a substitution estimator where eta hat is the MLA. So this isn't really, if you want to do things parametrically, the world is easy. You just have to have parametric models and be able to maximize the criteria. There's an interesting subclass of models, which is obviously the linear model. And this is interesting because it saves you from having to model the distribution of L and A. And so this can be avoided altogether by using GMMs. Okay, so I'm not going to discuss this, but I'm going to illustrate a simple case of linear models where you don't actually, I've already showed it. In fact, you just do two-stage least squares. So in the linear model that I presented earlier, it turns out one can show that the solution H is actually just a linear model in A, W, and X. Then one can estimate the average causal effect with a regression beta, coefficient beta hat A, obtained by fitting the standard linear regression, where you've just regressed W on A, Z, and X in the first stage, and you put it in here. So what are the properties of this? Importantly, just like in two-stage least squares, the model W hat need not be consistent for the mean of W given Z and A and X, for beta hat A to be consistent for beta A. Okay, as long as you use least squares for that first stage. We refer to this procedure as proximal two-stage least squares, given its close relationship to two-stage least squares estimation in the instrumental variable setting. And as mentioned earlier in the talk, W hat is a proximal confounding control variable. This connection, in fact, has implications for practice, as it reveals that the estimator can be implemented with any off-the-shelf instrumental variable software, which can perform two-stage least square for multivariate exposures, upon taking W as the endogenous variable and Z playing the role of the IV, with A and X taking as covariate. And I should point out here that you need not actually point identify the coefficients of W. So if you have more W's than Z, that's okay. Because at the end of the day, unlike in causal inference where we care about the coefficient, here we don't. We just use it for prediction purposes. Okay, so any estimator will do, it doesn't have to be unique. So let me quickly go over an analysis and then the example, I'm not going to revisit it. I'm just going to mention that there were 10 variables measuring the patient's overall physiological status that were measured using a blood test during their initial 24 hours in the ICU. So here are the 10 variables. These variables may be subject to substantial measurement error and a single snapshot of an underlying physiological status that may be viewed as potential confounding proxies. Among the 10 variables, we focused on 4 that were strongly correlated with both the treatment and the outcome, and thus we construct Z and W from this reduced set and collect all other variables in X. So these are physiology status measured from lab values, okay, from the blood samples. So we specify proxy allocation, 2 of them in Z and 2 of them in W, and just as a sanity check, we commuted them, and nothing really changed. The results were very stable, regardless of the choice of among these 4 proxies at least. So for estimation, we use a linear model, and then we apply two-stage least square using IV reg and R, where, as I said, you have 3 variables. A is playing the role of a covariate, W plays the role of the endogenous variable, and X is also covariate. Z is the IV for W. We run that. So here are the results. Oh, shoot, I'm sorry. I should have checked up the compiling. So the variable we care about is RHC. A negative value estimate refers to as a harmful effect. They had a harmful effect in just ordinary squares is just you adjust for the covariates, just like they did in the original. Although they use a propensity score, we just direct adjustment here in the model. And we found a causal effect as well, and it was also harmful. It was somewhat larger than the one that they found. You can also check for presence of unmeasured confounding. There was marginal evidence, and the way you check for that is you look at the coefficients for W in that regression, the proximal regression, and one of them was marginally significant, suggesting that there was residual confounding in this study that might explain the difference in the results, if in fact all the assumptions hold. Okay, so to do due diligence, you would want to use different proxies. We did, alternated their roles. The results were stable. You would also want to use less parametric assumptions, which we've done in a paper I will mention in a second. So let me just close, so in case there are some questions, we have a little bit of time. So we've described a new framework for the analysis of observational data subject to potential confounding bias. The approach acknowledges that in practice, measured covariance in observational settings generally fail to capture all potential confounding mechanisms, and at most may be seen as proxy measurements of underlying confounding factors. Our proximal causal learning framework provides a formal potential outcome framework under which one can articulate conditions to identify causal effects for proxies. Although we've used parametric models, we can also use less parametric models. We've used reproducing kernel Hilbert space and deep neural nets as well in ongoing work, and they seem to work quite well. You just have to be careful how you use them. As I mentioned, you can extend this to complicated panel data where you might have time varying treatment. I did 2 time points here. I have A0 and A1. I have time varying on measure confounding, U0, U1, some of which is U1 is on the causal pathway of the prior treatment. And so this is a complete mess. This is the most complicated longitudinal data you can ever encounter. And it turns out everything extends to this setting quite nicely. And finally, we've done some semi-connected theory and more MATSTAT type questions about establishing lower bound for estimating these objects when the root n is not possible. And so this extends higher order influence function theory, that work that I did with Jamie a few years back, to a setting where you have your nuisance parameter is not a condition expectation, is the solution to an inverse problem, okay, or to an integral equation. And then, as you can tell, the framework is pretty generic. So any setting in causality where you assume exchangeability, as it turns out, you can adopt these methods. Any set of frameworks where you relax endogeneity, you can still use these methods, and it sheds some light as to how you can make progress non-parametrically even in those setups. So they're listed here. I'm not going to really discuss this. Let me just finish here. This is work funded by three NIH grants of mine. I want to thank the PI group. I want to thank Jamie and Ilya for helpful discussion and a lifetime of inspiration. And this work is actually now posted on the archive. It can be downloaded. If you have any questions or interest in any other papers, feel free to contact me. Thank you so much.
Thank you very much. So we have time for questions. So I guess that at this point you can just unmute yourself and ask the question. Joan. Okay, let me go for it then. Like Eric, something that I'm not sure if I understand. Like the framework does or doesn't allow you to interchange the roles of W and C in your estimation. You do it in the empirical application. And
yeah, let me share my screen again so I can go to the. Thank you. That is a good question. So it depends on the setup, right? So so what I described earlier on. This is kind of why I presented this. So this is what is enough.
Mm-hmm.
In this case, you cannot exchange the role of Z and W, because if Z causes the A, you're screwed. You can't move Z to W. In this setup, Z doesn't cause A, W doesn't cause B.
Okay.
So if there's a choice of Z and W such that you can argue for this, you're good. Cases where you cannot argue for this is when you know for a fact, like in treatment by indication, you know for a fact that the lab values were used by the doctor to assign treatment. But often, you just have observational data that the patients don't have access to the covariance you collected when they made the treatment decision. And so this might actually be reasonable for a rich enough set of views. In which case, these Z and W can be turned around. It's perfectly symmetric.
Yeah. And the other thing that I have in mind, well, like another way in which people kind of approach this, like a failure of exchangeability, is like some type of sensitivity analysis. What that would be in this context?
Yeah, so that's a good question. So the key identifying assumption is are these ones. These are the ones you worry about.
Yeah.
So you can do a sensitivity analysis, kind of a la imbens, where you model U and you pick values for U and for the effect of U on YZ, and then you can run a sensitivity analysis incorporating some distribution over U.
Yeah.
It's pretty clunky. And you know, it's not the most. I mean, we haven't actually done it, but I would imagine that's what you would have to do. Just like people would run. Usually, they would just use a binary U.
Yeah, usually it's a binary U, a linear model,
exactly,
or something like that. Yeah.
Yeah. So what we have done in the case of the standard exchangeability assumptions, we've taken that model and we made it semi-parametric in the sense that you do have to model the magnitude of you do have to assume you know the magnitude of the effect of U on A, the treatment, and you do have to assume you know the magnitude of the effect of U on Y, but you can actually be completely non-parametric about the density of U. So in that setup, that's kind of appealing because you don't have to restrict yourself to binary U. You can assume some really complicated U and still get something simple and interpretable. But I imagine that's something like that you would want to do here as well, which we haven't done for this setup. What I was describing was for the usual setup.
Okay, thank you so much, Eric. With that, I think like our time is over, and I'm now going to invite everybody to unmute themselves and yes, like give you a hand like I'm going to do.
Thank you so much. It was great fun.
Thanks a lot. Thanks a lot for coming here. Thank you, Eric.
Thank you. Bye.